Right now, we're hot. We're popping them out. Water as a solvent. Let's go.
Still no intro. So, water as a solvent. We talked a little bit about this in class. Then, as part of your homework, you should have done all those four water charts. Not everybody did it, but you should have, and hopefully you will in time for the test. Of those four charts, I think the one that takes a little bit of a what am I trying to say? The one that takes is a little bit more difficult to understand is the water as a solvent. The other ones are basically just facts. Look it up, understand what's going on, and those of you who did the homework will already have a step up on that. So that'll definitely help you out. But I do want to touch on the idea of water as a solvent. So here I have drawn out a bunch of water molecules. Now, normally hydrogen is not green, but I wanted to go Christmas themed. So oxygen is usually red in models and representations and stuff like that. So I left it like that. So we have all these water molecules here. And to review, I would have drawn this out if I thought this before, but we're making it up as we go. To review, let's go over what a water molecule is. So I'll draw this jumbo water molecule out here. So we have that, and then our two hydrogens out here. Okay, we'll go to the more reasonable side. So then we have the connection, and as I've drawn many times, I'm going to make this mostly red, and then the last part of it will be green. Okay, so what am I trying to represent here? Well, right here is oxygen. Oh, that's fat. Undo. I undid way too many. Shoot, can't go backwards. All right, we'll roll with it. We're good. Okay, so this is oxygen right here, and then here we have hydrogen and hydrogen. Now, we talked about covalent bonds. We know what's going on here. Each line represents two electrons that are being shared so that they all achieve their happy octet. And meanwhile, oxygen has two lone pairs of electrons out there because it has 1, 2, 3, 4, and then each line is 2. So 2, 4, 6, 8, that makes it happy. Hydrogen just wants 2. In those lines, it has 2. So everyone's happy, they're covalently bonded. However, oxygen is still much more electronegative. So oxygen is more electronegative. We've talked about this. Negative. It's hard to write and talk at the same time. Oxygen is more electronegative, which means it's going to draw electrons toward itself more than hydrogen. So oxygen is more electronegative than hydrogen, and in this case, it means that all the electrons shared in these bonds, so the 2 electrons per bond, are going to get pulled this way more. Okay, that's why I drew the bond as mostly red, because oxygen is going to take over that bond, and that's going to make this end down here negative. This is your negative pole. Okay, the negative part of the atom. And then down here, this hydrogen is going to be more positive. This hydrogen is going to be more positive. As I said in the last video, they're protons on a stick. You took away their electron, it's just a proton. It's a proton on a stick. Protons are positive, so it's just sticking out there being positive. Okay, so that gives a water molecule its polar characteristics. Negative on one side, positive on the other, and then they're attracted to each other. So up here we have all these water molecules. Same thing going on. Oxygen, 2 hydrogens. The red dot, that whole side of the molecule is more negative. The green dots, the hydrogens, that side is more positive. So as these exist in water, you're going to have hydrogen bonding. That's what holds water together. So I'll start over here. This hydrogen is attracted to this oxygen, and this hydrogen is attracted to this oxygen, and this hydrogen is attracted to this oxygen over here. And then this hydrogen is attracted to this oxygen, this hydrogen is attracted to this oxygen, this hydrogen is attracted to this oxygen. You know, they're all over the place. They're attracted to each other. Okay, and that's creating the interactions that water has. Okay? So, however, to be specific, I do think it's only 2 hydrogens per, because what they're really attracted to, let me back up, are these lone pairs, the negative lone pairs. Okay, so I think specifically you can only have 2 hydrogens bonding, and I'm saying that with air quotes because it's not an ionic or covalent bond, it's an attractive force that we call hydrogen bond. We can only have 2 hydrogens per 1 water molecule, if we're being specific, and that's how they all line up with each other. Now, to get to what we're talking about here, as a solvent, like dissolves like. So you might have heard that before, we've said it before, but what does it really mean? Well, it means that in all of this here, so we're looking, this is like a cup of water, okay, or a beaker of water. Let's make it a rounded top here. So we got a beaker of water here, all these water molecules existing. Now, if I take a salt shaker, I don't really have room to draw, but if I had a salt shaker here, and I shook in a bunch of sodium chloride, what's going to happen? Well, we know from experience that if we put it in and we shake it up, or we mix it, that the salt's going to dissolve. Just like in ocean water, salt's dissolved in there. You don't reach through and pull up a ton of salt. It's dissolved in there. And you could take ocean water and boil it and you'll be left with salt, but that's because you're breaking the bonds that form. So salt is becoming dissolved in this water. So let's draw out some sodium chloride. NaCl. Okay. So NaCl. Let me just see here. So I'm just going to draw it as like this. So here's my negative chlorine. And then in blue, here's my sodium. And we'll connect them with a little line. Okay, so this is one example, or one molecule. Okay, it's drawn kind of weird, but that's okay. So you have your negative end and your positive end. So what's going to happen here? Well, I just erased all those hydrogen bonds because they're going to start to not necessarily break down, but there's a new guy in town, and he's a polar guy, okay? So once again, we have a negative and a positive part of this molecule. So it's going to be able to interact as well, and it's going to form dipole-dipole interactions like we talked about in the last video. Dipole-dipole, because you have a negative and positive. It's not hydrogen bonding anymore in this case because it's sodium and chloride. Your positive isn't hydrogen, it's sodium. So it's not hydrogen bonding, but this sodium is still going to be attracted to that oxygen. I'll do this. I don't want to do it in orange because that'll be the same, so I'll do it in, let's do pink. This sodium's positive charge is going to attract it to this oxygen's negative charge. And this chlorine's negative charge is going to attract it to this hydrogen's positive charge. So at the molecular level, or even the atomic level, really, because we have 2 separate atoms here that are separately charged, at the atomic level, this sodium chlorine is going to start interacting with the water. It's going to become one with the water, as Bruce Lee would say, be like water. It's being one with the water because it's forming bonds with the water. It's not just in there separate from the water molecules. It's not like surrounded by water molecules that aren't interacting with it. It's surrounded by water molecules that are interacting with it. So if we had another one in here as well, that would form bonds too. And I mean, I could draw a ton of these, okay? So again, this, whatever the closest hydrogen is going to be interested in this chlorine. And keep the same color. And this is going to be interested in this. And it's bonding. And they're forming these bonds with the water molecules. So when we say dissolved and you think of a glass of water with salt in it, you think of it on a macro scale, stirring it in and it's gone. But this is what's happening in the micro level, at the micro scale, with these tiny little atoms interacting with the other ones. And when these new molecules get popped in here, all the water molecules are like, ooh, who's this new guy in town that I want to hang out with? I want to check him out. We should hang out on the weekend. And it's weird. So, like I said, I could draw a ton of these all interacting, and then you still have some hydrogen bonding going on as well, with between other things, and all these interactions start working together. But the point here is that it becomes dissolved because these are interacting at the atomic level. Okay, so then to finish this up, just to show you, if I took let me think. Like some sort of gas, something that's non-polar. So two of the same thing bonded together. If I put Cl2 in here or whatever, something that shares electrons equally. So if I had purple something, and I'm going to keep the bond purple because it's just sharing these electrons completely equally. There are no poles here. There's no positive and there's no negative. It's non-polar. Okay, so this little purple thing I just dropped in is non-polar. So water's not going to be interested in this. Water doesn't care because this oxygen is not going to be interested in that non-polar thing. It doesn't care about it. It doesn't have a positive charge to interest the oxygen. It doesn't have a negative charge to interest the hydrogens. So this is just going to exist on its own, and this isn't going to have any water molecules interested in it. So the example I used in class is oil. If you put oil in water, it floats on top because there's no interactions going on. It's not going to dissolve. Or I don't know, you could think of dropping sand in water. It's not going to dissolve completely within the water. But if you took nonpolar molecules and you put them in a nonpolar solvent, then they're going to have London dispersion forces between them as the strongest interaction. And that's the interaction that'll be common to all of them. So they will become one, they will interact with each other. But as far as water goes, a nonpolar solute isn't going to get the job done. It's not going to interest water. It doesn't care about it, and it's not going to bond with it. It's not going to spend any time with it. They're not going to be friends. So you need a polar molecule to be dissolved in water because water is a polar solvent, and it's polar because you have this negative end and this positive end. And if you want something else to be interacting with a water molecule, then you need a positive end and you need a negative end so that they can form these interactions. Okay? That's why like dissolves like. Like dissolves. Did I spell that? I definitely. Okay. It's awkward. Like dissolves like. Okay? That's why. Because at the atomic level, it needs to be able to bond with whatever's in it if it's going to become part of it. Okay, so hopefully that clears up any confusion with that. I could keep going on, but I'm sure you guys get the idea by now. Thank you for watching. Definitely like and subscribe.